All right, guess it's ready. And you can see the screen now.
Yeah.
Okay. So, all right. Let's see. Do I have any idea what I'm going to talk about? So, right. I think at the end of our last discussion, I started talking about the idea. I can't remember at what level of detail I was suggesting it might work at. Whether it was just supposed to be an analogy or whether it's supposed to be a detailed correspondence of some kind. But I started suggesting that there's some connection between Grothendieck's children's drawings and the Jugendtraum, Kronecker's Jugendtraum.
Yep.
And I think I've got a lot more detailed ideas about that I want to tell you about. But I guess the first thing I want to mention is that at some point in the discussion last time, I think I heard you pronounce the word, I presume it's the word, French word, D-E-S-S-I-N.
Yeah.
I assume you're pronouncing it correctly, and it was a little bit different from what I was expecting, I think.
I don't know. Don't count on it being correct.
Oh, I kind of was. But okay. Well, anyway, even if it's incorrect, that's still interesting from my viewpoint. Because so you pronounced it like with a Z sound, design, I think.
Yeah, but I don't.
What?
Yeah.
So okay,
Yeah.
I have no idea whether that's right, but it suddenly reminded me of the English word design, and I don't think I'd ever really noticed that the idea of
Oh. Yeah, that sounds pretty.
I don't know. It could be
plausible.
complete coincidence, but so I mean, whatever Grothendieck called them, design, d'enfant, or something like that. I certainly got the impression that means something like child's drawing or children's drawing, or something like that, and in a sometimes futile attempt to keep or make mathematics accessible to the non-sophisticated mind, because I have a non-sophisticated mind. I like to keep it in English because I speak English. So I call it a children's drawing rather than a whatever it is, a dessin d'enfant or something like that. But somehow when you said design, and it made me think of design, that really set off something in my mind. It reminded me of when I actually was a child, that we called things like that design. We used to say we're drawing a design when we were in kindergarten or first grade or something like that. Did you ever use that vocabulary? Do all children use that vocabulary? A design?
Okay. I'm turning off my video.
Okay, yeah.
I don't remember doing it especially.
So I don't know why we called it that, but because it was just like a drawing, but we called them designs.
Like a geometrical type drawing that you do for you? You wouldn't use that for like a picture of a apple, would you?
I guess that's right. For some reason, I guess maybe we distinguish between pictures and designs. I don't know. And right, the designs I'm imagining, they didn't look all that different from. I mean, a lot of people drew very curly cube sort of filigree designs, but I think I did have a tendency to draw very angular, in some sense, more geometric designs or something like that. And yeah, so I have some weird, vague memories about this. But I like it. So in particular, I'm just calling these things designs from now on. I think that's my new terminology. Designs. What?
Yeah, I checked the etymology and it is connected, design and design. So.
I mean, that's strange that it's connected because the word designs looks so much like a French word. But maybe it's one of those things where, we inherited the word from French more than once, and it looked different the two different times we inherited it or whatever.
Yeah.
What's that?
There's a French word désigner,
Yeah,
a verb, which I guess
Yeah.
means something like to design. And it comes from Middle French désigner, which has a G in it.
right.
I can't pronounce these things.
Right.
Borrowed from Italian designare,
Uh-huh.
Latin designo, or designo,
Uh-huh.
designare. So I guess designate is probably also.
Sure. I mean, as you started talking about that, I started thinking about that. But
So, okay.
so tentatively, I'm calling them designs, and it helps me to think about them because it really reminds me of the designs we used to draw in kindergarten and stuff like that. And it's, I don't know, shorter, and it's also more similar to what Grothendieck said. So right. So I've been talking to my friend about this too, and it's a little bit hard for me to always remember how much I told you, how much I told my friend Simon. So that gives me an excuse to just kind of jump into this without trying to remember exactly where we were or something like that. So I'm going to make a definition here, I guess, which is, all right, so I'm assuming we already know what a design is, because we've talked about them, maybe under a different name. So I'm going to say what a Gaussian design is. So a design is Gaussian. So how do I state this definition? Well, so first of all, we have to, well, let's see. So we have this very vanilla Coxeter diagram that has this this very vanilla labeling that, you know, it's infinity on each labeling, which means there's no constraint on the order of the composite of the reflections. So, you know, a design is like an irregular tiling for this Coxeter group, and basically irregular basically means it's sort of like a tiling that's coarser in a sense than the universal one for this.
Do you mean to be nitpicky, just to make sure I know what's going on? Do you mean like the even subgroup of that or the whole thing? Sure.
Let's talk about that. Yes. I do vacillate about that sometimes because.
But I guess if you're sticking with like holomorphic stuff, you would tend to use the even part. Maybe you shouldn't, but.
Well, yeah, because I mean, there's this whole idea of, you know, how real algebraic varieties fit into the story.
Yeah.
And they do fit into this story in a very nice way when you deal with the, you know, so you have like these designs with boundaries.
Is that something people talk about? Or is that something you talk about?
Presumably, but again, I don't know under what name they talk about it. But I thought you and I had talked about it. But again, I might be getting mixed up that I talked about.
I don't even remember. No, I don't remember anything about that. So
really, that's interesting.
Some other guy.
All right, I'll have to tell you about that sometime, but I guess not right this second. So
okay. Anyway, go ahead.
So there's so there's another Coxeter diagram that's relevant here, which is I guess 4, 4, 2, except that, you know, the edges with label 2 are conventionally drawn invisible, so it's just, you know, drawn like this.
Yep.
And there's all sorts of ways to think about this particular Coxeter diagram. So I guess it's an affine Coxeter diagram, meaning, you know, the geometry is flat. And moreover, it's kind of like it's you know, this Coxeter tiling, this universal Coxeter tiling for this, it's the Voronoi tiling for the Gaussian integers. I guess we should do in tandem, to make the pattern clearer. we should also do another example, which is the Eisensteinian example, which is, which is 6-3. So this gives the Voronoi tiling for the Eisenstein integers, and this gives the Voronoi tiling for the Gaussian integers. So let's see. Maybe I should, right, sometimes I use color coding here. Maybe I should try to use color coding here. So let's see, how does this work? Let me think. It's like green and blue and red and we have those labels 4 and 4. And so what is the tiling? What does the universal tiling look like? It kind of looks like let's see. Let's see. I get very confused here by a sort of Poincare duality type thing. So let's see. What am I trying to say? The red dots, the red vertexes in the tiling, I think those are supposed to be, yeah, I think those are supposed to be the centers of the Voronoi cells. And that'll be the same pattern over in the Eisenstein case. So in the Eisenstein case, we'll have green, blue, and red. And maybe I'm making a stupid mistake here by not reminding us that we've actually talked about this before, right? When we were talking about abelian surfaces and the Nearand-Severi groups, and we got into the thing about how the Nearand-Severi group has a Jordan cone structure, and that led into this stuff that we were.
Yep. That was connected. Yeah.
And yeah, and we wrote down these Coxeter diagrams, except that we had over towards the right, we had an extra vanilla edge, which made it into you know, a thing involving 3-dimensional tilings, and it gave a hyperbolic tiling of the Jordan cone for these very particular Gaussian and Eisenstein abelian surfaces with complex multiplication. So that was about abelian surfaces with complex multiplication, and it related to these Coxeter diagrams. Here we're dealing with just with elliptic curves with complex multiplication, and particularly nice ones, right? These are the Eisenstein one and the Gauss one. It's better than just complex multiplication. It's got this symmetry. And yeah, so that other stuff actually had to do, right, with taking one of these elliptic curves with complex multiplication and then getting an abelian surface by squaring that elliptic curve. And, you know, the Nearand-Severi Jordan cone and the hyperbolic geometry of the, you know, Lorentzian mass hyperboloid, or whatever you call it, energy hyperboloid inside the Jordan cone or something like that, led to these Coxeter diagrams, which were related to the, you know, the Voronoi tilings of the Eisenstein and the Gaussian integers, but they had these extra 4th dots. But right now we don't have the 4th dots. So it's just, what am I trying to say? It's like 6 and 3 over here. So, right, hopefully when I draw them and put the color coding in, it helps to see what's going on here. So what am I trying to say? So let's see. I guess I'm drawing Voronoi cells. I guess that means I should put the reds in the center of the Voronoi cells. So let me put in a little bit more here. So the reds are actually the Gaussian integers.
Okay.
Whereas the greens are like, the deep holes in the Gaussian integers. So, right, I think, right, there's some general obvious fact that, what am I trying to say? The vertexes of the Voronoi cells is a synonym for deep hole or something. According to somebody's terminology. I think that agreed with the way they used the terminology when I looked it up. And let's see. So the blue dots will be barycenters of edges. And so those will be, all around here.
Nope.
What's that?
Yup. Sorry, a mixture of a yawn and a yup.
Sure. And, and then when you put in the whole barycentric subdivision, it looks like what? It looks like, and then you can see all the Coxeter tiles after I put in all the barycentric subdivision lines. Am I doing this right? There's still a series of lines that I haven't put in yet, right?
Yes.
So
if you really want to know, the 2 blue dots you haven't put in yet.
2 blue dots I haven't put in yet. Okay, I see one that I haven't put in yet. Okay.
Yeah.
And
oh, yeah.
do that right? Right.
So.
I shouldn't be too scared because I do have, the good eraser thing here. So
yeah. Yeah.
So, let's say the Gaussian integer 0 is right there. So, the Gaussian integer 1 is right next to it. And the Gaussian integer I is right up there. And
the Gaussian integers are just the red ones, right? It looks like you're pointing at a blue one, but.
No, I was trying. Yes, I'm sorry. You're right. You're right. Sorry, that was a mistake. Yes. So yes, the Gaussian integer 1 is right there. Yes. Gaussian integer 1 is right there. The Gaussian integer I is right there. The Gaussian integer 0 is in the middle. Okay.
Yep.
So let me try to draw a little bit of the Voronoi tiling for the Eisenstein integers. So what does that look like? The Voronoi cells are hexagons. Is that right?
Yeah.
So the integers themselves will be red, the deep holes will be green. So what have we got? We've got a red, and then it's inside a hexagon or something like that. And I'm drawing this very badly freehand, but it's gonna be something like this. Doing this right? And yes. So those are the deep holes. And
but you're drawing it in some way where 1 is sort of slanted down. One is.
Say that again. I didn't understand what you said. Say it again.
You're drawing it so that the number 1 is going to be not on the same.
Oh, okay, that wasn't intentional.
Yeah. So if you'd wanted.
All right. Okay. I'm willing to redraw it. I don't know if I have a thing that.
I think you should draw the red dots first if you want to come out looking.
Okay. Let's try that.
Like the usual picture of the Eisenstein integers.
Okay, we'll try that. So let's see.
Well, you're not leaving much room. Woo. Okay.
Really? All right. Okay. Yeah, I'll take a look.
Yeah, I mean, look
a
at
little
what
bit
happened
more.
with the Gaussians. You started out with the reds, and then by the time you drew all the other stuff, it got pretty damn busy.
Sorry. What am I doing here? I don't know exactly how this works, but all right. And then you're telling me the deep holes are like in there. And then all right, so let me put in the actual Varnai cells. And then the edge barycenters are like there. Doing that right?
Yep.
Well, doing it sort of right, but very sloppy. And okay, so it's like there. So you can think of the rotation group. Am I doing this right? You can think of the rotation group as being the semi-direct product of GL1 acting on the additive lattice. Did I say that right? GL1 of the number ring, GL1 of the Gaussian integers is Z mod 4. GL1 of the Eisenstein integers is Z mod 6. That all seems more or less correct.
Yep. Sounds right.
And I'll just circle
Very,
the origin. What?
Very, very digressively.
Yes.
It would be sort of fun to see how G2 gets into this game here, because it's also acting.
Yes. No, that's not that digressive. You just said you're talking about G2, right?
Yeah.
Yeah, there's something G2. I'm not sure I ever noticed this, the G2-ishness of the Eisenstein integers. Have you thought about that before? By the way,
No,
you said
I
there were
haven't.
2 missing blues. Are there more missing blues here? Let's see.
Okay.
I wonder if it was the same too. So what were you saying about G2?
Well, some of the dots you just drew are a subset of the dots you just drew are the G2 root vectors, and the G2 Coxeter group, which is bigger than the A2 Coxeter group, acts on this picture you're drawing over here at left. So anyway, there could be some cool octonionic stuff hiding out in here, but I really haven't explored it.
I think
we have sort of thought about it once we were like thinking about how the G2 picture you can think of as like a picture of an octahedron viewed compressed down to the plane. This is like a perspective picture of an octahedron if you view it in a certain.
Yeah.
And that octahedron has to do with B3 or maybe C3. Somehow and that 8-ness of the octahedron actually has to do with the octonions. Yeah. So anyway, yeah, there's this weird stuff. Anyway.
All right. I'll have to
I'm
think about
getting
that
too digressive,
later.
but
But I did at least notice that, there was something G2-ish going on here.
yeah,
But
yeah.
but I'll really need to stare at the picture more later to understand the G2 aspect better. But so what am I trying to say here? That this lets us talk about a design being Gaussian or Eisensteinian.
Namely,
That so let's say a design is Gaussian, respectively Eisensteinian, if and only if, let's say, it's maybe it's called the canonical triangulation. If it's canonical triangulation is coarser than, in a hopefully sensible meaning of coarser, is coarser than the 4-4 triangulation. Respectively, in the Eisensteinian case, it would be the 6-3 triangulation. So I stated that definition very sloppily, but I hope you're getting the idea. So I mean, right? So basically, you can think of a design as, you've got the free group on two generators, and you've got a finite transitive action of it. Right, and you can associate that finite transitive action with a conjugacy class of finite index subgroups. Those finite index subgroups are the stabilizers.
Yeah.
Of the, I guess it's called the cells in the design.
The what?
Well, I said cells, but there's a couple of different kinds of cells. I guess these are those sort of double cells that they call lozenges or something like that.
So now you're going to say that if it factors through the affine thing?
Yes, that there's some, and I'm hoping there's some sort of, Noether's theorem here or something that says something rather convenient. What am I trying to say? That, if I have a subgroup of this Gaussian Voronoi group, that's basically a what? That's basically a subgroup of the free group on two generators that's larger than the normal subgroup that you get for the kernel of, projecting the free group on two generators to the to this Gaussian Voronoi group. And you do that sort of in the obvious way. I mean, that you right, you just map the one Coxeter group to the other Coxeter group by, I guess maybe I should have used the same green, blue, red coloring for the dots in the Coxeter group that gives you the designs.
I think I cut out there for a while, unless you weren't saying anything.
Well, then can you tell me, are you happy with the definition yet?
Yeah, I'm happy. I think, well, yeah, yeah. It depends how carefully I try to be happy. But
right. We're not trying to be super careful, but I'm hoping you heard what I said about. What?
I have a very precise concept in my mind, and I may
Okay.
not actually understand what it's like well enough. That's the problem.
And you heard me say something very casually about the Noether's theorem and the subgroup that's larger than a normal subgroup.
Yeah, I heard all that stuff. So I get
Okay.
that stuff.
Okay. So so that is a definition of what a Gaussian design is, and correspondingly a definition of what an Eisenstein design is. And the motivation for these definitions is roughly this. Well, do you want to guess what the what the motivation is? Is it
No, I mean,
okay?
give me a
Yeah.
clue. If you give me a hint about, I mean, what kind of direction you're trying to go, I might be able to guess. But
Well, I mean, I prefaced this by saying that I was, trying to link up
okay.
Kronecker's Jugendtraum with
Okay.
with Grothendieck's designs. But maybe I should have. Well, so should I try to?
Well, so
Okay.
anyway, that must be something about that you're gonna like try to hook up Kronecker's Jugendtraum for elliptic curves with these two particular quadratic
Right. For the
fields.
moment, for the moment, it's so far just these two particular elliptic curves. It could be that maybe we should somehow get it to work for much more general elliptic curves. Maybe even ones just with complex multiplication, or maybe even ones just arbitrary elliptic curves.
So I have
Yeah.
a possibly relevant stupid question, which is that so that infinity Coxeter diagram.
Yes.
And it's a group. It would map onto any triangular Coxeter group.
That's right.
And so you picked two that were planar or affine Dinkin diagrams. Is that right? No, sorry. Yes.
Yeah. I guess they're called affine Coxeter groups. They're certainly related to affine Dinkin diagrams in some funny way. That's part of the G2 story, I think. But I don't want to worry about that.
Okay, well, anyway, affine Coxeter groups. But you could have done it for some hyperbolic ones or for non-affine ones. So you could have like picked weird big numbers.
Yes. Yes.
And I'm just wondering, like, could that stuff be related to other number fields or something? I don't know if I even want
number
that.
fields or something. There's all sorts of possibilities. But it could also be that we might want to use other subgroups that don't really come from, or other quotient groups that don't really, subgroups or quotient groups, I don't know. There's all sorts of possibilities, but I mean, what you're suggesting is definitely interesting. I mean, in particular, well, I mean, you didn't say that, the modular, PSL to Z is one of these hyperbolic Coxeter groups. And it's very interesting to try to figure out how that fits in.
Yeah.
But
okay. Anyway, I just wanted to mention that they're like, you're picking two mountain peaks, but there's like tons of other.
Sure.
Other ones.
Sure. But there's particular reasons for picking these two. And so roughly the motivation is this. That, I mean, maybe it's obvious, but let me say it anyway. That, a big focus of interest in understanding Grothendieck's designs is understanding this alleged Grothendieck-Teichmuller action of the absolute Galois group on it, on something, maybe on the designs, maybe it might, there's supposed to be this action that takes one design to another, but then there's other ways you can interpret what Grothendieck-Teichmuller action is here, which probably really has to do with Teichmuller's aspect of it, the having marks, extra marks on a curve. So what am I trying to say? That roughly speaking, the motivation for these definitions of the Gaussian and the Eisensteinian designs is that it seems natural to conjecture, and I hope it's actually true, that Kronecker's Jugendtraum can completely account for the Grothendieck-Teichmuller action on these Gaussian and Eisensteinian designs. So that's the idea.
Okay.
So, I mean, we need to describe that in much more detail. But I mean, for one thing, I hope it's sort of obvious that this is an attempt to make something much more precise out of the vague ideas I was suggesting at the end of the last discussion, to make an analogy between the Jugendtraum and the designs, or particularly the Grothendieck-Teichmuller action on the designs. So, you know, the hope is the usual sort of hope, that when you have a bridge between two topics here, that you can work it in both directions, that you can transport whatever your understanding is from either end to the other end. So, you know, there's a lot of things that are seem easy for me to understand about Kronecker's Jugendtraum, particularly in this case of the Gaussian and the Eisensteinian case. And I can try to transport that understanding over to help me understand what the Grothendieck-Teichmuller action is all about. For the most general designs, or even more general than that, the whole whatever this whole alleged concept of Grothendieck-Teichmuller theory is, that perhaps Drinfeld developed or something. Again, I don't know the history of it, but so that's the rough idea. And so in particular, yeah, so what am I trying to say here? That well, so Grothendieck-Teichmuller theory is also it's supposed to be all about the action of the absolute Galois group on some stuff, some intuitively accessible stuff. Kronecker's Jugendtraum is also about the action of the absolute Galois group, or some absolute Galois group, on some stuff. But it's but in the Kronecker's Jugendtraum case, it tends to be about just parts or co-parts of the absolute Galois group that are either abelian or actually sort of close to abelian, just being like metabelian, but at a very low level. Metabelian meaning, I think when you have I'm hoping that metabelian means something like just an iterated an iterated. Maybe metabelian means it's got like a Jordan Holder tower or something like that, and all the stages in the tower are abelian or something like that. But in the case of Kronecker's Jugendtraum, particularly applied to elliptic curves, it's just this very first level of the metabelian tower. They just have
Isn't that thing you
Yeah.
just described, isn't that
Yeah.
thing you just described solvable?
All right, then. Okay, so maybe metabelian means what I was talking about. Maybe it just means two-stage solvable. Is that possible? Metabelian maybe means two-stage solvable.
I don't know.
It doesn't matter, but yeah, I guess you're
Yeah.
right. I guess you're right that I should have just been, I totally somehow the terminology solvable just for some reason totally escaped me for a moment there.
Anyway,
so yeah,
I just cheated and checked, and you are right about your latest guess about metabelian. So
metabelian means two-stage solvable. Yeah, and so that's kind of what happens with Kronecker's Jugendtraum. The first stage is just the abelian Galois group, the absolute abelian Galois group, right? The absolute abelian Galois group, which is just really the Kronecker-Weber stuff that has to do with the cyclotomic fields, and then the imaginary quadratics with complex multiplication, they live, or even without complex multiplication, they live inside of that cyclotomic stuff. And so then if you use those, if you now relativize and use those as the new starting point for the abelian stuff, that's where the Jugendtraum comes in. So you're at that metabelian level, that two-stage solvability thing. Yeah. So in that sense, Kronecker's Jugendtraum is much less ambitious than the Grothendieck-Teichmuller theory, because the Kronecker's Jugendtraum is very low in this solvability hierarchy, and in particular, it doesn't even, right? I mean, there's this whole solvability hierarchy, but that doesn't even get you to the really interesting thing where there are simple groups that appear in the Jordan-Holder. So Kronecker's Jugendtraum is it's very close to the abelian end of the pool, but perhaps it's getting just a little bit of toe in the water towards the non-abelian end of the pool, because you're getting this second abelian stage, the metabelian stage. So you're still very far from the general absolute abelian group, which isn't even solvable. But you're, like I say, you're getting your toe in the water towards the non-abelian end of the pool. Right, so that says that, right, when you've got this relationship between these two areas, that one of them is much less ambitious and it's much easier, and it's historically earlier, which is presumably why it's much less ambitious. So that's sort of the easy end of the pool, and so that's where I sort of am right now, right? I mean, I'm trying to understand these Grothendieck-Teichmuller theory, but but for the moment, I'm very near the easy end of the pool, the shallow end of the pool, the abelian end of the pool. But I am getting my little toe in the water towards the non-abelian end. That's part of what's going on here. That's part of what's going on here.
Yep.
But on the other hand, there's also something very intriguing about the shallow end of the pool, the Kronecker's Jugendtraum. That really, at a very naive level, it gives me hope of trying to really it gives me all sort of dreams. I mean, I get, so let's see, what's Jugendtraum mean? I guess it means dream or something like that. Yeah.
Youth,
So,
yeah. Maybe Elternstraums.
right. There's all that stuff about different dreams for people of different ages or something like that.
Starting out with infants.
Right. So right. This whole thing is an analogy between youths and children or something like that.
Yeah.
But I'm not right. It's very confusing because in French, infant doesn't sound so young, but in English, infant sounds really young. Yeah. So I'm not sure how young a youth is, et cetera. But maybe it's all the same thing: youth, children, infant, whatever. Well, I keep on saying that Kronecker's Jugendtraum is like a sharpening, an improvement on the art and reciprocity theorem, completely oblivious to whether that's historically backwards or historically forwards or whatever. I just don't know what it is historically. But there's a certain sense in which conceptually Kronecker's Jugendtraum is sharpening and making much more explicit statements that are part of the art and reciprocity theorem. And the art and reciprocity theorem is, in some sense, a very complete description of absolute abelian Galois groups in pretty great generality. When I say absolute abelian, these are like relative absolute abelian Galois groups that the art and reciprocity theorem tells you about. But the art and reciprocity theorem, I mean, even it's like I say, it's in some ways it's a very complete theorem about it, how it tells you to understand this absolute abelian Galois group of the number field, and it tells you it in terms of stuff that lives inside the number field itself, in some sense, like ideals in the number field and things like that, or ideals in the ring of algebraic integers inside the number field, or fractional ideas. It tells you a whole lot about the absolute abelian Galois group, but Kronecker's Jugendtraum sharpens and improves upon that because it gives you very explicit ways to generate the abelian extensions of the number fields to which it applies. But it perhaps doesn't, as far as I know, it doesn't apply to as many number fields as the art and reciprocity theorem applies to. The art and reciprocity theorem pretty much applies to arbitrary number fields. That's one of the things that's so great about it. Whereas the Kronecker's Jugendtraum does something better than what the art and reciprocity theorem does, but only does it in special cases. These number fields that are that are totally imaginary or something like that, or maybe ones that live inside totally, I don't know. But I guess what I'm saying is that the extra information in the Kronecker's Jugendtraum compared to the information in the lesser information in the art and reciprocity theorem, as I understand it, is really nice extra information to have, but it's nice when you can get it. You can't always get it, perhaps, or at least in my understanding, I don't understand how it could be as general. But also, so both the art and reciprocity theorem and the Kronecker's Jugendtraum and all the generalizations of, well, I shouldn't say all the generalizations of Kronecker's Jugendtraum, but the easy generalizations of Kronecker's Jugendtraum are very abelian. It's the whole theory of abelian varieties with complex multiplication and stuff like that. But, one of the things you can dream about is getting beyond the abelianness restriction, right? You can dream about generalizations of Kronecker's Jugendtraum that aren't restricted to just thinking about abelian extensions. And this way that we're trying to set up a way to think of the Kronecker's Jugendtraum as a part of Grothendieck theory suggests that to me. I mean, maybe I just, maybe my whole understanding of everything here is too naive, but that's the way I'm thinking of this. I'm thinking that, hey, it almost seems like this Grothendieck theorem, Grothendieck theory, it almost seems like that is a fulfillment of this dream that I have always had about getting something that's like Kronecker's Jugendtraum, like the theory of abelian varieties with complex multiplication, except way better because it works for non-abelian extensions as well.
So is the thing that's like the variety supposed to be the branched cover of the Riemann sphere? The thing that's supposed to be like the elliptic curve?
That's part of it. That's part of it. But I'm not sure, because there's some confusion between, you've got these branched coverings, and I'm not sure. I always get confused whether I should be looking at the base of the branch covering or the total space of the branch covering. And so probably yes, but
I was hoping you would be like
Yeah.
looking at the something like the function field on the branched cover is like some extension of the function field on the base, and so you somehow use that to get like a number field that's extending some other number field. It's a little vague how you do that part. But
yeah, but also, but I was gonna say, what are we going to use as the base? I mean, I mean, we could just use as the base this Riemann sphere with 3 marked points. I'm not sure I caught everything you said. Did you say what? Should you say it again? What?
So I was thinking you were trying to get like an explicit description of an extension of an algebraic number field in the similar way to how the Jugendtraum gives it to you. And I don't even understand that well enough, by the way. But so here,
right? But that's part of the point. I'm like I said, this is a bridge for understanding, and you take it in both directions. So right. So yeah. Even if it seems like even if it seems like the Jugendtraum end is sort of the shallow end of the pool, it's still actually really good for learning that too. That's part of what I'm claiming. That's one of the things I neglected to say.
Yeah.
So go ahead. Yes.
Yeah. So blundering on. So
yes.
I would like to imagine like we start with some number field and we're trying to understand its algebraic extensions as like a concrete way of thinking about Galois theory. And so we think of that number field as sitting inside the field of functions on the Riemann sphere, or maybe the 3-punctured Riemann sphere. And then we get this branch cover of the Riemann sphere. And so that branch cover will give an extension of the function field of the 3-punctured Riemann sphere. And then so we try to lift our algebraic number field, which is sitting in the function field of the 3-punctured sphere, up to this. Well, we extend it along. It's like some kind of pullback square thing I'm imagining here, where like 2 of them are number fields and 2 of them are function fields. something like that. So that you try to get like explicit representatives, explicit description of the extension of your original number field in terms of specific functions on the branch cover. I guess that's just me trying to slap together all the ideas in a way that
I'm not sure. I'll have to think about that.
Yeah.
I mean, certainly things like that, ideas like that are floating around here, but I'm not sure to what extent the ideas I'm trying to describe are really doing that. I'm not sure.
Okay.
I mean, seems like we're suggesting all sorts of things. So one thing is this: supposing you have a design, one of these Grothendieck's designs, okay? Then that means that it is not necessarily defined over the rational numbers, but is defined over some algebraic extension of the rational numbers. And, you know, the minimal, I hope I'm saying this correctly. I hope I'm getting close to saying this correctly, that the minimal algebraic extension of the rationals over which the given design is defined. You know, defined means that you can write down the system of equations for it using coefficients from this base field, over which it's defined. So the minimal algebraic extension over which it's defined is, I think that's called something like the field of moduli, or the moduli field of the design. Okay. And it sort of sounds like we want something that goes in the other direction. Like maybe we want to say, if you start with a number field, then is there some functorial universal example of a minimal or canonical design which has that number field as its moduli field? It sounds like we might want that or something like that. I mean, I thought this was sort of implicit in something that you might have been suggesting.
Yeah, sounds like
and that this would be some sort of generalization or cousin of this idea of starting with an imaginary quadratic number field and obtaining, in a semi-functorial way, an algebraic variety, an elliptic curve on which it acts by complex multiplication or something like that. So that would be the raw material for I mean, are you saying? I'll really have to think about this, but for a moment I thought maybe you were saying that there is some generalization of complex multiplication here, that we can get an arbitrary number field to like act in some sense, some generalization of complex multiplication on some cover or covers here. So I don't know, but sorry. So at the moment, I'm very confused about a lot of this stuff. So I should probably just go ahead and try to talk at a lower level and do examples and stuff here so we can try to figure out what's going on.
Okay.
So, well, but one thing I should say is that in this analogy or whatever it is that we're trying to develop, that torsion points on elliptic curves with complex multiplication, you know, those torsion points are the things that look like some quotient ring of a number ring. Those torsion points on elliptic curve with complex multiplication. Those are supposed to be playing some role that's related to the role of the vertexes in our designs. And I mean, it should. You know, again, it's better. This part of it is better than just an analogy. And so let's try to do some examples here where we actually see some designs, some specific designs that would be related to these Gaussian and Eisenstein number fields. But I mean, maybe it's obvious that, I mean, right, we've already, I mean, right, you could just take, I mean, this picture that I've, is it clear where my cursor is pointing over here?
No.
All right, I'm somewhere.
Usually it is, but right now I don't see it at all. Oh, there, yeah, I see it. Okay, it's in the midst of all that stuff. Yeah, okay.
Okay. So, I mean, if we just make a, I mean, I guess we could do this example right here, right? We could just say that we're going to identify the top and bottom of this little grid here. So, you know, like this is maybe A, let me do it in a different color or different non-color, black. So we're just identifying A at the top with A at bottom and identifying B at left, B at right. So we've now got a one of these designs. And it's living on this Gaussian elliptic curve. And it's right to like the, if we just take just the, I'm trying to figure out what colors we should focus on. Maybe we should focus on the reds. So you know, because those are the centers of the Voronoi cells. So the reds are the, you can think of them as the three torsion points on this Gaussian elliptic curve.
Okay. Yep.
Now, these aren't the only, you know, these very, not every Gaussian design, according to my definition, not every Gaussian design, according to that definition, lives on an elliptic curve. Because, right, there are some things that are coarser than this group. Let me try to wrap this one up. Let me try to, I'll make an attempt to draw what happens when you wrap this, when you sort of mod out by the fourfold rotation symmetry here, right? We should be able to do that, right? That should be well defined. If we just wrap this up by the fourfold rotational symmetry. So what's that going to look like? So I'm going to try to do this. So there's like a red in the middle, and it's got, what is it? What has it got? So I've got like a blue and a green. Like that and like that. Are you any good at visualizing this or drawing this, what this looks like? So let's see. I mean, right, there's 8 rays emanating from the origin, but after you mod out by the fourfold rotational symmetry, there should just be 2 rays. So it's kind of like a ray. Yeah. Right, and one of them's sort of the diagonal one, and the other one's the rectilinear one, or something like that. So I guess the blue, the thing with the blue, the left half here is the rectilinear stuff, and the right half is the diagonal stuff, I guess. So are all greens in the same orbit? Let's see. Were there 2 different? Let's see.
Are you just modding out by a fourfold symmetry or? Yeah.
I'm trying to do that. That's what I think I'm trying to do. Why?
Okay. Well, I'm just trying to understand what's going on. So then you're going to wind up having 3 reds.
3 reds. That sounds right. And how many greens? And how many blues?
I don't know.
Let's see. I see 1 green.
Maybe. I think 4 greens.
You know what? Maybe I can cheat here. Maybe I'll make it do an easier one. Let's see. Should I try just, 2? So what would that one look like? That's right. Let's see. What does it look like? Just going after. Right. What if we do this one? Just
So then you're going to mod
roll
out
this one up. What's that?
Yeah, you're going to mod out this guy.
Yeah. So now I think I can use the same picture, right? I mean, so far I've now changed my mind about which one I'm doing. So, but I think I've still got the same picture so far. Because I may be cheating here because I may have actually tried drawing this example before. So it looks like there's only 1 red. Is that right?
Yeah.
No.
Yeah, if you mod out by a fourfold symmetry, there'll be just 1 red.
Well, but I think I screwed up because I put a green in the middle instead of a red in the middle.
Well, you did. That's true. I was wondering about that. But I mean, you could do it, right? You could still do that one.
Well, okay. Let me see. Green. So I'm putting a green in the middle this time, you said? And a red over there. See, I have a feeling that these ones that are wrapped up, they might be useful in understanding the Grothendieck-Teichmuller action. I'm not even sure about that, but that's my excuse for thinking about this one and trying to draw it. Since I don't have much time left, I may give up on trying to draw it, but I'm just going to make a very brief attempt to draw a little bit more of it here. So let's see, we have green. Yeah, so again, the green to the red, that's sort of the diagonal. And so how many greens are there now? Because we're right, there should be probably a different number of greens than reds because the center of the rotation is a green. in this example. So, right, it seems like I'm being very casual about getting mixed up between which ones, in the Gaussian case, it's easy for me to get mixed up between which ones are the Gaussian integers versus which ones are the dipoles.
Right.
And I probably just accidentally screwed that up, but it's okay because in the Gaussian case, unlike in the Eisenstein case, the dipoles look just like the Gaussian integers, or they look a lot like it.
Yep.
So, so there's just one red, is that right? But there's probably two greens.
Yep.
And maybe I can draw the green.
Three
over
greens.
there. Say that again?
Or three greens. There's the one in the middle. There's the one on the edges. And there's the one on the corner. Of this big.
Okay. So you think there's like the three greens are like that?
Maybe.
And there's just one red, we think. And how many blues are there?
I would say two.
Two, really?
I see another. Yep, that one.
So you're saying there's one there, and then you're saying,
Oh, well, maybe three actually. Yeah.
I can't tell. Is it two or is it three?
I think
This
it's
one
three.
is the same as this one. I think it's two, right? Because, am I saying that right?
No, if you're just modding out by a four-fold symmetry and they're 8 at that same distance, there's going to be, from the origin, you're going to be left with 2.
How can that be? Let's see.
And where does this edge go up? It's going off into outer space in your picture down below, and it probably ends on a blue. Or do you saying it just like wraps around and they can't, no, there's got to be a blue on that horizontal line that you drew in that picture down at the bottom. I think there's got to be another blue there. So you go across, you go green, blue, green.
Well, but I see 4
red.
blues in the middle, right?
Yeah.
I mean, in my original picture, I see 4 blues in the middle. And
Yeah.
then I see 8 blues around
Yeah.
the outside. And the 4
Right.
blues in the middle, that's obviously all one blue under rotational symmetry.
Yeah.
But isn't the 8 blues outside, isn't that all the same point?
You're just modding out by a 4-fold rotational symmetry, so you can't make 8 things be the same.
No, I'm modding out by that, but I'm also modding out by the, top equals bottom and left equals right.
Yeah, okay, then you're right. Yep, you're right.
So I think, let's see, I think there has to be something like this here. So I mean, right, this red dot has to have a lot of edges coming out of it. So far it's got 6, but there should be some others coming out of it like that, I think. Now it's got 8 coming out of it. And so what's happening? Red, green, and maybe I can draw the other blue. Let's see. Green, blue, green. Where did I put the other blue?
Right there, yeah.
Put a blue right there?
I think so. And I think that line that's going off to the right horizontally and fading out at the very far right of your picture, I think that like loops around back to that blue.
Could be. Could be. And maybe this goes here?
Oh, I don't know. Maybe.
Maybe this is it. Maybe this is it. Maybe this is it. I mean, that looks to me, right on the very outside, there are 2 big red, blue, green triangles. And then in the middle, everything is red, blue, green. Anyway, I'm hoping that this picture is actually the wrapping of this picture over here.
So how
By
come two of those greens just have two edges coming out of them, but one of them has four edges coming out of them? Is that really supposed to be like that? Maybe it is. So they're not all created equal. I guess that could be true.
Are they both? We have two greens that are both fixed under rotation? I guess that's right. There's the green in the middle, which only gets two, and there's also its antipodal green, which lives at all four corners, and that's also fixed under the fourfold rotation. So that it also ends up with a shortage of, its eight
Okay.
edges get reduced to two edges.
Okay. Okay. Yeah.
But wait a minute, no, but now I'm confused. So then we have the others. How did those get reduced from 8 to 4? Is there some rotational symmetry that explains? I mean, one possibility could be that I just totally screwed it up and didn't draw it correctly. And maybe we shouldn't worry about that too much right now. But I'm still hoping this is correct, but it might not be. So, right, but it's clear that these are actual designs.
Yeah, if we ever figure out how to draw them right. Yep.
Right.
Yeah.
If we ever figure out how to draw them correctly, they are actual designs. And
Designs that we don't know how to draw.
so there, right. So there, I think we have just enough time left for one big punchline if we don't screw it up. And this one big punchline is roughly, well, it's supposed to leave us with hope for this general project of using this alleged bridge of understanding between these two topics. The topic of Kronecker's Jugendtraum on the one hand, and the topic of Grothendieck theory on the other hand. So it's going to leave us with that hope. But more specifically, what it's going to do, hopefully, is this going to teach us, maybe particularly you, I mean, probably me too, because I'm not sure how well I understand it to begin with, but it's going to teach us something about how Kronecker's Jugendtraum really works. And so what am I trying to say here? That Kronecker's Jugendtraum is, boy, there's so many ways to say it here. I'm not going to succeed in saying all of them at the same time. So, but somehow you are supposed to understand them all at the same time somehow. But the Kronecker's Jugendtraum is all about how the absolute Galois group acts on the torsion points on this elliptic curve with complex multiplication. So what am I trying to say here? That see, and the way it acts is by by multiplication in the number ring, multiplication in the Gaussian integers. So yeah, right, somehow multiplication in the Gaussian integers am I saying this right? So okay, let's think about sorry, let's think about right, the Gaussian integers modulo 3, right? So that has a lot to do with this picture over here, right? It sort of the Gaussian integers modulo 3 live as the green vertexes on this picture of this Gaussian elliptic curve. By the way, are you still connected? See, now I can't tell whether you're still connected. Maybe you're having connection problems here, which,
Yeah, I am connected, but I'm having lots of problems. Can you turn
Okay.
off your video?
then
Let's see.
again, turn off my video. That's what you said.
Yeah, I think your screen sharing will still go on, but
All right, I just have to try to
it
figure out
seems
how
to
to
be
do
like-
that. I just have to try to figure
there
out how to
should
do
be
that.
there should be a little picture of a camera at the bottom.
Okay, okay,
Okay, let's see if this works better.
okay. Okay, and you can still see the,
Yep.
yeah, I do actually miss video. The video does help me when I see your face, but,
Yeah.
so let's see, what am I trying to say? Well, so I'm staring at this picture over here, which is, you can think of this picture in a whole bunch of ways. It's like the 3 torsion points on the Gaussian elliptic curve, but that's related to the Gaussian integers modulo 3, right?
Yeah.
So in the Gaussian integers modulo 3, so I guess what I'm saying is, one of the things I'm saying is that GL1, comma, the Gaussian integers modulo 3 is bigger than GL1, comma, the Gaussian integers, or modulo 3 or something like that. Right, because there are scalars in the Gaussian integers that are not invertible, but that become invertible after you mod out by 3, namely 2. I mean, there might be others as well, but certainly there's 2.
Uh-huh.
So that's giving us extra symmetries of the set of Gaussian integers modulo 3.
Is the Gaussian integers mod 3 the field with 9 elements?
I guess it is, but you have to, but you're relying on something special to think to, right? I mean, it wouldn't be true if it were the Gaussian integers modulo 5. That wouldn't be the field with 25 elements, right? Because right, there's like this whole pattern in the Gaussian integers that when you mod out by something that's 4n plus 3, like n equals 3, n equals 0, which would give 4n plus, which would give 3, 4 plus 0. That you get a field. Whereas if you mod out by something by 4n plus 1, then you get a product of fields. So you get the 5-element field squared if you mod out by 5, whereas you get
Oh, okay.
the 9-element field if you mod out by 3. So right, and that's a big part. All those patterns is a big part of what we're trying to understand here. Although that's sort of in the base. We're trying to understand patterns that are analogous to that, but that are starting from a higher base, starting from the Gaussian integers itself. So what am I trying to say here? That right, we have this Coxeter rotation group, and multiplication by 2 does not, it doesn't give us an element in the Coxeter group, but it does act as a symmetry of this Coxeter group, except it's right, it only acts as a, am I saying this right? It only acts as a symmetry of the group, but it doesn't act as a symmetry of the Coxeter structure. So it's going to change the shape of things, or it has the potential to change the shape of things here. But okay, but we're still trying to understand the Jugendtraum here. What am I trying to say? That think about what it means to be a primitive 3 torsion point in on a primitive 3 torsion point on the Gaussian elliptic curve.
Okay, what?
And it's supposed to be just like analogous to thinking like a primitive 3rd root of unity, right? The point is that algebraically you can't distinguish between distinct primitive 3rd roots of unity. They are in the same orbit under the absolute Galois group. So it's going to be the same thing here, like with I'm saying, there's nothing you can, once you've said that a number is a primitive 3 torsion point on the Gaussian elliptic curve. When I say a number, I really mean the coordinates of that point on the Gaussian elliptic curve. And you know, because you can express, you know, the multiplication on the elliptic curve algebraically, you can write down equations that describe the coordinates. You can write down algebraic equations that describe the coordinates of the primitive 3 torsion points on the Gaussian elliptic curve. But right, it won't factor into linear factors. It will be some higher. It will factor into some, or I guess it will be irreducible. I guess because there's not, right. Once you've said that you've got this primitive 3 torsion point on the Gaussian elliptic curve, you said all you can say about that point. You can't distinguish the different primitive ones from each other, just like you can't distinguish algebraically the different primitive 3rd roots of unity from each other. And it's kind of funny, right? Because in a visual geometric way, you can easily distinguish the 2 3rd roots of the 2 primitive 3rd roots of unity from each other, right? One of them lives in the upper half plane, and one of them lives in the lower half plane. So you have some sort of geometric intuition that enables you to distinguish between them, but there's nothing in the algebraic language that lets you distinguish between them. So Kronecker's Jugendtraum is telling us, that multiplying by these Gaussian integers that are relatively prime to the Gaussian integer that we're modding out by is giving us these Galois symmetries. Right, so what am I trying to say? Right, I mean, I'm trying to say this, that I mean, to go back to the cyclotomic example, right? If you take, you know, your favorite primitive 3rd root of unity, and you multiply it by itself, you get your anti-favorite primitive 3rd root of unity. And it works the same way with these torsion points on, right? The primitive, the roots of unity are just the torsion points on the multiplicative group.
Yep.
So we're doing something very analogous here, and we are right. If you think about what we're saying, we're really just saying that you can get the other primitive. You can get the other primitive 3 torsion points on the Gaussian elliptic curve just by multiplying by these Gaussian integers that are relatively prime to 3. So in other words, we're saying that the absolute Galois group here manifests as this multiplication by the Gaussian integers that are relatively prime to 3 here. And that's what the Grothendieck-Teichmuller action is. That's how it's manifesting on these Gaussian designs. And that's very specific information. I mean, we'll have to try to explain this better the next time we talk, or whenever we talk about this. But that's what I'm trying to say here, that I'm trying to describe how Kronecker's Jugendtraum tells us very concretely how the absolute abelian Galois group, or the relative absolute abelian Galois group, manifests in terms of its action on the torsion points on the Gaussian elliptic curve, for example. And it manifests just by this multiplication by Gaussian integers that are relatively prime to the thing that we're modding out by. And that is this very easy to understand special case of the Grothendieck-Teichmuller action. And if we could elevate our understanding, well, so we have to develop, I'm claiming it's easy, but I'm claiming it really is easy to understand this action of the absolute abelian Galois group in this Jugendtraum context. It's just this thing that I'm saying, the multiplication by the things that are relatively prime to the thing that to the Gaussian integer that we're modding out by. That is right. That's giving us a very concrete manifestation of the absolute abelian Galois group, and that's really what the art and reciprocity theorem is telling us about, and it's what Kronecker's Jugendtraum is telling us about. But then we see this as a special case of the whole Grothendieck-Teichmuller theorem, and we try to, bootstrap our way up in that way. So we're gonna develop this understanding of Kronecker's Jugendtraum and the art and reciprocity theorem in this very straightforward way. And then the plan is to try to bootstrap this up into a grand understanding of the whole Grothendieck-Teichmuller theory. And it seems like at some point this Grothendieck-Teichmuller theory has to sort of meet with the Langlands program somehow. So secretly we're also trying to understand the Langlands program in here. And it's very naive and very ambitious, but that's kind of where we are. Is that's not completely meaningless, right? That you can sort of see where I'm trying to go with this. Is that right?
Yeah, I can sort of see. I would like us to do more of an example of what we were just.
Yes. That's what we want to do. We want to do some really concrete examples. So that should be our starting point for next time.
Yep.
Okay.
Okay.
I hope that was sort of okay in terms of trying to explain where we're going here. Okay. But thanks a lot. I'll see you.
Okay, see ya.
Okay.
I got it.
Bye.
Bye.